For all of recorded science, matter has seemed permanent, stable, and quietly eternal. Yet deep inside modern physics lies a startling possibility that one day even the proton itself may vanish. And if that is true, then everything built from atoms, from stars to planets to life, may be far less permanent than it appears. So before exploring this profound mystery, please like the video and subscribe to the channel for more journeys into the hidden laws of the universe. At the widest scale, the universe presents itself as a place of immense duration rather than sudden change. It appears about 13.8 billion years old, and across that span it continues to expand, carrying galaxies away from one another, while preserving a broad, large-scale order that remains visible in deep surveys of the sky. Astronomers look outward and therefore backward in time, and the farther they see, the more they witness matter, enduring across almost the whole known history of the cosmos. Light from remote galaxies begins its journey when the universe is young and arrives after billions of years, still carrying the signature of atoms that absorb, emit, and hold their identity over astonishing spans of time. In this outermost view, matter does not seem fragile. It seems patient. It seems able to remain present while the geometry of the cosmos stretches around it. The great map of the sky reinforces this impression. Galaxies gather in clusters. Clusters line up along filaments, and between those filaments lie enormous dark intervals where matter is thinly spread. Even so, the visible universe is not a scattered ruin. It is a connected structure whose luminous parts reveal long continuity. Many galaxies are themselves ancient, with ages reaching close to that of the cosmos as a whole. Their light shows that ordinary matter has persisted through changing eras of expansion, cooling, merger, and motion without giving any sign that its substance is quietly dissolving away. What changes on these scales is arrangement. Galaxies drift, groups collide, clusters grow, and space expands. But matter itself appears to remain available to take part in each new pattern. From the outermost perspective, the cosmos seems less like a blaze that consumes itself and more like a vast, slow reshaping of material that endures. This impression of endurance begins very early. After the hot beginning of the universe, conditions cool enough for simple atomic matter to emerge, and from that stage onward the visible cosmos carries familiar substance forward through time. Vast stretches of gas remain between galaxies and within them. Later luminous structures appear, but even before those structures become common, the universe already contains the material from which long cosmic history proceeds. Across billions of years, matter passes through many environments and many temperatures, yet on the larger scale it continues to exist in a form that can still be recognized by its interaction with light. A line in a spectrum seen across a great distance is a quiet statement that matter remains matter. The same basic kinds of atoms identified nearby are also identified in ancient light, and this continuity gives modern physics one of its deepest forms of confidence. The outer universe may be remote and dim, but it does not look chemically alien in its foundations. It looks stable enough to be traced across time. Because of this, the large-scale cosmos teaches a subtle habit of thought. It encourages the idea that matter is not merely common but durable in a very deep sense. A mountain erodes, a world cools, a cloud disperses, a galaxy changes shape, yet these are changes of form rather than vanishing of substance. The visible record of the universe supports that quiet expectation. Matter enters new settings, but it does not seem to step out of existence. The observer looking across cosmological distance therefore meets not a scene of continual material loss, but a scene of continuity under transformation. This does not mean the universe is static. Expansion continues, structures evolve, radiation travels outward, gravity gathers matter into new concentrations and leaves other regions sparse. Still, beneath all this motion lies an assumption that feels almost unavoidable from the outer view. Ordinary matter lasts. The cosmos behaves as though its material ingredients are dependable enough to cross nearly the full age of the universe without failing. That sense of endurance is reinforced by the way astronomy itself works. Modern instruments do not merely detect distant light. They compare, sort, and interpret that light through patterns that depend on matter, behaving the same way across time and distance. A line produced by hydrogen in a nearby region can also be recognized when it arrives from an era billions of years earlier, shifted by cosmic expansion but still unmistakable in identity. Matter leaves absorption, emission, mass, motion, and structure behind as readable traces. This makes the universe feel legible. It is not only old, it is coherently old. The same material order seems to persist long enough for observers in one late galaxy to reconstruct events that unfold across most of cosmic history. That would be impossible if ordinary matter were constantly slipping out of existence on accessible timescales. That assumption grows stronger when present experimental limits are placed beside the age of the cosmos. No confirmed observation has shown proton decay, and the most sensitive searches continue to report null results. With lower bounds on proton lifetime in key channels extending beyond 10 to the 34 years, future detectors are being built to push that reach even farther. From the standpoint of the large-scale universe alone, this means the visible substance of galaxies, gas, and worlds appears not merely old, but extraordinarily secure on any timescale that astronomy directly confronts. Compared with 13.8 billion years, the present experimental limits point toward a kind of practical permanence. Matter, as the sky presents it, does not seem to stand near a cliff edge. It seems to rest in a condition of almost immeasurable endurance. Even the oldest light strengthens this impression. When observatories study ancient radiation and distant galaxies, they do not uncover a cosmos where matter has been fading away unnoticed. They uncover a cosmos in which material history remains legible. The same broad physical language applies across distance and age. Matter bends light through gravity, leaves spectral marks, forms extended structures, and persists long enough for the universe to build complexity on top of it, again and again. In the widest frame, the cosmos presents continuity before doubt. Its darkness is not emptiness of meaning, but a vast setting in which matter appears calm, lasting, and deeply reliable. Beyond the widest map of the universe, matter becomes easier to recognize in its working forms. It gathers into gas, dust, and stars. These are the visible materials that give the cosmos texture and brightness. Between stars lies the interstellar medium, a thin mixture of gas and tiny solid grains spread across vast distances. Most of this gas is hydrogen, with helium next in abundance, while heavier elements are present in much smaller amounts. The dust is a minor fraction by mass, yet it has an outsized role in shaping cosmic light, dimming some regions, reddening others, and helping cold clouds shed energy so that they can contract. In this setting, matter is not arranged as fixed architecture. It drifts, cools, warms, glows, and gathers. Even so, it continues to exist in forms that remain identifiable across immense stretches of time. Interstellar space is often imagined as empty, but it is more accurate to see it as extremely thin substance spread through a very large volume. In some regions, the gas is hot and sparse, heated by violent events and energetic radiation. In others, it is cooler and denser, especially inside molecular clouds where atoms join into simple molecules and the light grows faint behind veils of dust. These clouds can extend across many light years, while remaining cold enough for matter to settle into denser pockets. The motion is slow, shaped by gravity, turbulence, magnetic fields, and starlight. What stands out is not haste, but persistence. The gas does not vanish simply because it is thin. It endures, shifting from one physical state to another while staying part of the material inventory of the cosmos. Astronomers trace it through radio emission, infrared glow, and absorption lines, and again the message is continuity. Matter remains present long enough to be mapped, classified, and followed through changing environments. Within the coldest and densest parts of these clouds, stars begin. A cloud fragment loses pressure support, contracts under its own gravity, and slowly turns gravitational energy into heat. At first, the forming object is hidden, wrapped in gas and dust. Later, when the central temperature rises high enough, nuclear fusion begins and a star enters a long stable phase. This is one of the clearest expressions of cosmic endurance. A star is not a brief spark in the ordinary sense. It is a regulated balance between inward gravity and outward pressure from hot gas and radiation. As long as that balance holds, the star shines steadily. For a star like the Sun, this stable period lasts about 10 billion years. For smaller red dwarf stars, theoretical models indicate lifetimes that can extend far beyond the current age of the universe. Matter, once gathered into a star, can therefore remain in a coherent luminous state for spans of time that rival or exceed the histories of planets and civilizations by an almost unimaginable margin. This long stellar stability gives matter a second kind of permanence. It is not only that atoms survive, it is that large reservoirs of matter can remain organized, hot, and radiating for billions or even trillions of years. A star spends most of its existence converting hydrogen into helium in its core with remarkable steadiness. The rate depends strongly on mass. Large stars consume their fuel quickly and live shorter lives, while smaller stars burn much more slowly and remain stable for far longer. In every case, the star shows that matter can hold form under extreme conditions. Temperatures rise to millions of degrees, densities increase toward the center, and pressure becomes immense, yet the material world does not dissolve into chaos. It follows durable laws and preserves structure. This is why the night sky, whether seen nearby or at great distance, appears filled not with transient disorder, but with repeating, stable sources of light. The interstellar medium and stars are joined in a slow exchange. Stars form from clouds, then later return part of their material to space through winds, outflows, and for the most massive stars, explosive endings. This exchange does not reduce matter to absence, it redistributes it. Hydrogen that once drifted invisibly in a cloud may spend millions or billions of years inside a star, then return to space mixed with newly formed heavier elements, carbon, oxygen, silicon, iron, and many other elements are built in stars or in their depths, and then cast back into surrounding gas. Later generations of clouds inherit that enriched material. Dust grains condense from heavy elements in cooling outflows and become part of future clouds and future stars. This long circulation gives the cosmos a feeling of continuity without rigidity. Matter changes role while preserving presence. It passes from diffuse gas to shining star to drifting remnant material, yet it remains part of the same broad physical story. Light makes this endurance visible. A star's spectrum reveals what its outer layers contain. Emission from nebulae shows which atoms are present in surrounding gas. Infrared observations reveal cold dust that does not shine brightly at visible wavelengths. Radio observations expose hydrogen distributed through space in regions that would otherwise remain hidden. By comparing these signals, astronomers see not a disappearing substance but a persistent one moving between states. Even when stars age and clouds disperse, matter leaves behind observable traces. A red giant's wind, a planetary nebula, a supernova remnant, and a dark cloud each show different temperatures and densities, yet all belong to the same enduring inventory of cosmic material. The sky, therefore, appears less like a place where matter is lost, and more like a place where matter is carried through long transitions. The forms are temporary. The substance seems reliable. This reliability matters for how physics thinks about the world. The visible universe contains stars that are very old, gas that survives between generations of star formation, and heavy elements that remain available long after they are forged. These facts do not prove that every constituent particle is absolutely eternal, but they strongly support the practical assumption that ordinary matter is extraordinarily long-lived. If it were otherwise on accessible timescales, the stellar and interstellar record would look less coherent than it does. Instead, the cosmos presents a layered history in which matter repeatedly participates without obvious depletion. Clouds remain capable of forming stars. Stars remain capable of shining for vast periods. Their remnants remain capable of seeding new clouds. The observed order depends on continuity measured not in years or centuries, but in millions, billions, and, for some stars, far more. Seen in this region alone, matter appears deeply trustworthy. It drifts through cold darkness, condenses into stars, radiates for ages, and returns to space without losing its identity as part of the cosmic substance from which visible structures are made. The interstellar medium holds the raw material. Stars hold it in luminous balance. Together they reveal a universe in which matter is not static, but enduring, not frozen, but faithful to long cycles that remain legible across immense reaches of time. On the scale of galaxies, matter takes on a form that is neither as diffuse as the widest cosmic web, nor as intimate as a single star. A galaxy is a great gathering of substance held together over immense spans of time. It contains stars, gas, dust, stellar remnants, and a surrounding gravitational environment that helps preserve the system as a coherent whole. Seen from afar, a galaxy appears almost serene. Its light forms a quiet shape against darkness. Whether that shape is a spiral with curved arms, an elliptical glow with smooth boundaries, or a smaller irregular form with no simple symmetry. Yet beneath that visual calm lies a slow and continuous movement of matter. Stars orbit, gas drifts, dust gathers in lanes and clouds. New stars appear in some regions while older stars dominate others. Even with all this motion, a galaxy remains recognizable across billions of years as a stable home for matter rather than a brief arrangement soon lost to emptiness. This endurance matters because a galaxy is not a single object in the simple sense. It is a long-lived system made from countless smaller parts, each with its own timescale and physical state. A spiral galaxy may contain hundreds of billions of stars spread across a broad rotating disk, with a central bulge of older stars and a faint surrounding halo. Gas settles into clouds within the disk, especially along spiral arms, where density is slightly enhanced and star formation becomes more likely. Dust traces the colder and denser regions, often marking the places where fresh generations of stars begin. Elliptical galaxies show a different character. They hold less cold gas, contain older stellar populations, and appear smoother, with less obvious internal contrast. Even so, they remain great reservoirs of matter that persist over long epochs. In either case, the galaxy serves as evidence that matter is capable not only of lasting, but of remaining organized on a scale that stretches human imagination. The interior of a galaxy is not static. Stars move through the gravitational field in ordered orbits that can take hundreds of millions of years to complete. In a disk galaxy, the inner regions orbit more quickly than the outer regions, yet the system does not tear itself apart. Gas responds differently from stars because it can compress, cool, and collide. Dust rides with the gas and helps shape the thermal balance of dense clouds. Stellar explosions and winds return material to the interstellar medium, adding energy and newly formed elements. All of this makes a galaxy active in the slowest possible sense. It is always changing, but the changes are distributed across such long intervals that the whole system conveys continuity more strongly than upheaval. Matter does not appear to be slipping away from existence. It appears to be circulating through a durable structure that can persist for much of cosmic history. Galaxies also preserve history in their form. Their stellar populations contain records of earlier epochs. Older stars dominate some regions, while younger and hotter stars mark places where gas has more recently condensed. Chemical composition varies from one part of a galaxy to another, revealing where generations of stars have enriched the surrounding material with heavier elements, globular clusters, ancient star groupings bound tightly by gravity, often accompany large galaxies and testify to very early phases of galactic assembly. Extended halos of sparse stars and gas show that a galaxy reaches farther than its brightest visible region suggests. In this way, a galaxy is both a present structure and an archive of slow material change. Its matter remains present long enough to store layered evidence of its own past. Mergers and interactions add another dimension to this endurance. Galaxies do not remain forever isolated. They pass near one another, exchange tidal forces, distort each other's shapes, and sometimes merge into a new system. At first glance, such events might seem like destruction. In practice, they are better understood as rearrangement. Stars usually pass one another without direct collision because the distances between them are so large. Gas clouds can compress and trigger new star formation. Dust is stirred, stretched, and redistributed. Long tidal streams of stars may be drawn out into surrounding space. Over time, the disturbed system settles into a fresh equilibrium. Matter changes location and pattern, but again, it does not simply vanish. Galactic collisions reveal that even violent structural change does not imply material disappearance. The substance of a galaxy proves resilient enough to survive transformation and take part in new long-lived forms. This resilience shapes the appearance of the visible universe. When telescopes look deep into space, they find galaxies at many different stages of development. Some are small and irregular, some are actively forming stars, some are massive and comparatively quiet. Across this diversity, the common fact is that matter remains available to build, rebuild, and sustain galactic systems. A galaxy can consume gas through star formation, receive new gas from outside, lose some material through energetic outflows, and still persist as a material structure for billions of years. The balance changes from one era to another, but the broad continuity remains. Galaxies therefore strengthen the impression, already given by the larger cosmos and by stars themselves. Ordinary matter behaves as though it is extraordinarily long-lived. The visible order of galaxies depends on that fact. There is also a quiet lesson in the sheer scale of galactic mass. A single large galaxy contains enough ordinary matter to form vast numbers of stars, planets, clouds, and remnant objects. This material is spread through regions so large that light itself takes tens of thousands, or even hundreds of thousands of years to cross them, depending on the system. Yet despite that scale, the galaxy holds together as a meaningful unit. Gravity provides the large framework, but the continued presence of matter is what gives the framework visible form. Without long-lived matter, there would be no enduring stellar disk, no ancient halo population, no accumulated dust lanes, no chemical enrichment across generations. The galaxy would lose its role as a stable container of cosmic history. Instead, what is observed is the opposite. Matter remains present long enough for galaxies to mature, interact, and age while still retaining coherent structure. For this reason, a galaxy can be seen as one of the clearest demonstrations that matter appears dependable across deep time. It is not merely that individual particles are assumed to last. It is that entire populations of material objects remain in relation to one another for billions of years. A galaxy rotates, evolves, accretes, merges, and settles, all while preserving a recognizable identity. The stars within it are born and die on different schedules. Gas clouds thicken and disperse. Dust forms and is destroyed and forms again. Yet the galactic whole continues. In that continuing whole, matter behaves as a patient substance, capable of moving through many states without surrendering its underlying presence. At this galactic scale, the observer meets a universe that is structured not by momentary flashes but by durable assemblies. Galaxies stand as long-lived provinces of matter, where substance is distributed, recycled, and preserved over immense intervals. They do not suggest fragility, they suggest continuity. They show that matter can inhabit a large gravitational order and remain there, not perfectly unchanged, but steadily present, carrying the visible cosmos forward through age after age. At the scale of planets and moons, matter takes on a quieter and more intimate durability. It no longer appears mainly as drifting gas or as stellar light. It becomes ground, ocean, cloud, ice, and air. A world forms within the disk of material that surrounds a young star, where dust grains and larger fragments collide, stick, and slowly gather into bodies large enough for gravity to shape. Over time, many small objects become fewer large ones. Some remain as asteroids or icy remnants, others grow into planets. In the warmer inner regions of a planetary system, rocky worlds are more likely to emerge, built from silicate material, metals, and other heavy substances that can remain solid at higher temperatures. Farther out, where colder conditions preserve more ice and gas, larger outer planets and icy moons can take shape. In either setting, matter does not merely persist as free material, it settles into worlds with surfaces, layers, weather, and history. A solid world has a different kind of permanence from a star. It does not shine by its own fusion. It endures by holding form, gravity rounds it, sorts its interior, and keeps its material bound together over immense spans of time. The early stages may be violent, impacts are frequent, surfaces melt, young atmospheres may be lost and replaced. Yet after this unsettled beginning, many worlds enter long eras of comparative stability. A rocky planet cools from the outside inward, crust forms, basins, plains, and highlands appear. Volcanic activity reshapes some regions while leaving others ancient and still. A moon may preserve scars from an early bombardment for billions of years. An ocean world may hide water beneath a shell of ice for ages too long to picture easily. These are not momentary expressions of matter. They are enduring arrangements that remain recognizable across deep planetary history. The diversity of worlds deepens this impression. Some planets are bare and heavily cratered. Some are wrapped in thick atmospheres. Some hold active volcanoes. Some carry liquid water at the surface, while others preserve it as ice or conceal it below. Moons add further variety. They can be geologically quiet, or they can be pulled by tidal forces into continuing internal motion. Yet all of these differences rest on the same broad fact. Matter is able to gather into coherent bodies and remain there long enough for each world to develop its own stable character. A planet is not simply a heap of material. It is a place where matter acquires geography. Mountains, plains, valleys, polar caps, cloud layers, and seas all testify that substance can persist long enough to be shaped by gravity, heat, chemistry, and time into something lasting. Rocky worlds make this especially clear because their surfaces carry the visible memory of endurance. A crater may remain for immense spans where erosion is weak. Lava plains can harden and remain exposed long after their heat is gone. Continental crust on Earth survives in parts for billions of years, even while erosion and plate motion continue to modify it. Desert rock on Mars keeps signs of an older climate. Ice on outer moons preserves fractures and ridges under dim sunlight far from the warmth of the inner system. Matter on these worlds does change, but often very slowly. Wind, water, ice, impact, and tectonic motion reshape the surface, yet they do so by moving and transforming material, not by erasing its existence. The same atoms of rock may pass from mountain to sediment to seabed to uplifted stone, while remaining part of a world that endures. Atmospheres extend this endurance into a softer form. Air seems less permanent than rock, but on planetary timescales an atmosphere can also last for astonishing intervals. Even as its composition shifts, it can circulate heat, shape weather, carry dust, drive erosion, and protect or expose the surface below. A thick atmosphere can hide the land entirely, as on Venus, where clouds veil the surface from ordinary sight. A thin atmosphere can leave a surface stark and exposed, as on Mars, where dust and cold dominate. Earth's atmosphere and oceans operate together in a continuous exchange of water, carbon, and energy, linking sky, sea, ice, and land into one persistent planetary system. Even when atmospheres are lost, replenished, or chemically altered, the process again reveals endurance through change. Matter remains in circulation, moving between surface and sky, between interior release and exterior loss, between liquid, solid, and gas. Oceans reveal another form of planetary steadiness. Water at the surface or below ice transforms a world by storing heat, dissolving minerals, moving sediment, and moderating climate. On Earth, the hydrologic cycle carries water through evaporation, condensation, precipitation, runoff, and return, tying the atmosphere to the ground and sea in a system that never quite rests. Elsewhere in the solar system, water appears as vapor, ice, buried ocean, frost, or ancient channel marks. This variety shows that worlds do not need to be identical to express the same truth. Matter can remain present and active under many different conditions. It can freeze, flow, circulate, and settle while preserving the existence of the world that contains it. Large planets show endurance through scale as much as through surface. Their gravity holds thick envelopes of gas for billions of years. Their moons gather into families. Rings may appear and fade, yet the planet remains a long-lived center of material order. Rocky planets show endurance through surface and geology. Ocean worlds show it through hidden or exposed water. Airless bodies show it through preserved scars. Across all these forms, the same lesson returns. Matter is able to become world-like. It does not simply drift through space. It assembles, differentiates, cools, and persists. By the time matter reaches the scale of a planet or moon, it has become something that can be walked upon, eroded, flooded, frozen, cracked, buried, or uplifted. It becomes landscape. It becomes atmosphere and coast and stone. It becomes a durable setting in which slow processes can work for ages without exhausting the material itself. Planets and solid worlds therefore stand as calm testimony to the long reliability of ordinary matter. They show substance not as a passing spark, but as ground that holds, seas that return, air that circulates, and ice that waits beneath the light of distant suns. Within worlds that have already formed and cooled, matter takes on another kind of endurance. It becomes record, rock, ice, water, and old landscapes preserve the passage of deep time not because they resist all change, but because they change slowly enough to carry memory forward. A crystal can remain locked in stone for billions of years. A layer of sediment can settle at the bottom of an ancient sea and still be read long after that sea is gone. Ice can hold traces of older air. River valleys, cratered plains, deserts, and worn mountain routes can retain the marks of processes that unfold across spans far greater than a human life. In this region of the story, matter appears stable enough to remember. Minerals offer one of the clearest signs of this quiet durability. A mineral is a naturally formed solid, with an ordered internal structure and a definite chemical composition within a limited range. Once formed, many minerals remain remarkably persistent if surrounding conditions do not become too hot or too reactive. Quartz, feldspar, zircon, and many other minerals can survive long transport and repeated geological change. They may be lifted, buried, heated, fractured, weathered, or carried by water and wind, yet their inner identity often persists. In the oldest known terrestrial zircons, some grains endure from early in Earth's history, more than 4 billion years ago. They are tiny objects, but they carry a message. The material world can remain present long enough for a single grain to outlast oceans, atmospheres, and continents. Rocks extend this endurance into larger bodies. An igneous rock hardens from molten material. A sedimentary rock forms from particles or chemical deposits laid down layer upon layer. A metamorphic rock is older material remade by heat and pressure without fully melting. Each kind of rock stores a different kind of temporal record. Igneous rock preserves cooling. Sedimentary rock preserves accumulation and changing environments. Metamorphic rock preserves transformation under altered conditions. The key fact is that none of these states represents disappearance. matter passes from one geological arrangement to another while remaining available to carry traces of what has happened. A sandstone may begin as grains weathered from older mountains. A slate may begin as mud on an ancient seafloor. A gneiss may begin as an earlier rock, later compressed and reheated deep within the crust. Matter remains stable enough to be handed from process to process without losing its presence. Layered landscapes make this persistence visible. Sedimentary basins collect mud, sand, lime, ash, and other deposits in ordered sequences that can stretch through immense spans of time. Later uplift can expose those layers at the surface, where cliffs, canyons, and coastal faces reveal stacked records of older worlds. One layer may represent a desert, another may represent a shallow sea, another may represent river floodplains or volcanic ash settling from the sky. The composition changes, the grain size changes, the color changes, yet the broader lesson remains simple. Matter stays, it accumulates, it hardens, it waits. When erosion cuts through these layers, the planet opens material that has been present all along. Water is often treated as the agent of change, yet water also belongs to the record of endurance. It wears rock down, carries sediment, dissolves minerals, and helps build new deposits. At the same time, it persists through cycles that are ancient on planetary terms. Water moves through ocean, cloud, rain, river, groundwater, ice, and vapor, then returns again. It may be stored in aquifers for long intervals. It may freeze in glaciers and ice sheets. It may seep through stone and slowly alter landscapes. Even when it reshapes the land, it is matter in motion, carrying other matter with it. A canyon carved by a river is therefore also a sign that matter can participate in long circulation without being lost from the world that contains it. Ice adds a quieter form of preservation. In cold regions, snow compresses into layered ice that can survive for hundreds of thousands of years or more under the right conditions. Each layer traps part of the atmosphere, part of the dust, part of the seasonal rhythm of snowfall and melt. Ice sheets and glaciers flow slowly, deforming under their own weight, yet they still preserve older material within them. Their endurance is not absolute. They advance and retreat with climate. They fracture, melt, refreeze, and move. Still, they show that matter can retain layered memory even while in motion. The cold does not halt time, but it slows many processes enough for material history to remain legible. Ancient surfaces deepen the same impression. On worlds with little erosion, an impact scar can remain visible for billions of years. On Earth, where wind, water, chemistry, and tectonic motion are more active. The oldest exposed surfaces are rarer, yet ancient cratons preserve some of the oldest continental roots. These stable interior regions show that large masses of rocky matter can endure through repeated cycles of uplift, erosion, burial, and change. Mountain belts rise and wear down. Rivers shift. Coastlines advance and retreat. Deserts spread and contract. Beneath these changes, old crust can remain, carrying the deep physical continuity of a planet across vast spans of time. What matters in all of this is not that materials resist every force. They do not. Rocks crack, minerals dissolve, ice melts, water escapes to vapor and returns as rain. Landscapes are cut down and rebuilt, but these are changes of arrangement, state, and location. They do not suggest that ordinary matter is inclined toward quiet disappearance. On the contrary, the history preserved in materials suggests the opposite. Matter remains dependable enough for time to write upon it. A planet could not preserve ancient mountains in worn roots, ancient seas in limestone, ancient ash in fine layers, or ancient climates in buried ice unless matter endured long enough to hold those marks. In deep materials, the world therefore appears calm in a special way. It is active, yet patient. It is changeful, yet continuous. A grain survives transport, a crystal survives burial, a rock survives alteration. A continent preserves its old interior, ice holds a layered trace of earlier air. Water returns again and again through long circulation. Across all these forms, matter shows a quiet faithfulness to existence. It allows time to pass through it without surrendering the record altogether. In that sense, the oldest materials of a world do more than last. They testify, in silence, that ordinary substance is stable enough to carry history across the immense and unhurried span of planetary deep time. Living matter introduces a quieter paradox. It is delicate, restless, and brief when compared with stars, planets, and ancient stone. Yet it depends on a depth of material stability no less profound. A living body does not endure by remaining unchanged. It endures by continuous exchange. Water enters and leaves. Gases are taken in and released. Molecules are built, altered, broken down, and rebuilt. Cells divide. Tissues repair. Energy flows through ordered chemical pathways. Life therefore appears active in every moment. But this activity is possible only because the matter within living systems behaves in reliable ways. The bonds that hold molecules together form under definite conditions. The same elements take part again and again in the chemistry of growth, structure, storage, and repair. In living matter, durability does not appear as stillness. It appears as trustworthy recurrence. Most of the material of life is made from a narrow set of elements. Carbon provides the backbone for a vast range of organic molecules. Hydrogen and oxygen are abundant in water and in many biological compounds. Nitrogen enters amino acids and nucleic acids. Phosphorus helps build hereditary material and energy-carrying compounds. Sulfur appears in some amino acids and helps stabilize protein structure. Other elements are present in smaller amounts, including metals that living systems use for transport, catalysis, and regulation. This select group is not random. It reflects a chemistry that is flexible enough to support complexity while stable enough to preserve form. Life is therefore not made from exotic substance. It is made from ordinary matter arranged with extraordinary care. Water gives this chemistry its setting. In a living cell, water is not merely an ingredient. It is the medium that allows molecules to move, meet, dissolve, separate, and react. It carries ions, moderates temperature, and helps determine the shape and behavior of the large biological molecules. A cell remains alive only while this watery environment stays within a narrow range of conditions. Even so, the water itself participates in cycles that are ancient and continuous. The same substance that fills oceans, clouds, rivers, and ice also fills cells and tissues. Life does not stand apart from planetary matter. It is a specialized arrangement within it. The chemistry of life remains possible because ordinary matter is stable enough to move from rock and sea into metabolism without losing its fundamental reliability. Carbon chemistry makes this arrangement especially rich. Carbon can bond to itself and to many other elements in varied ways, allowing chains, rings, and branches of great diversity. From this flexibility come sugars, fats, proteins, and nucleic acids. Each class of molecule has a distinct role. Carbohydrates store and supply energy and also contribute to structure. Lipids form membranes, store energy, and participate in signaling. Proteins act as structural fibers, transporters, receptors, and enzymes. Nucleic acids store and transmit hereditary information. None of these molecules is permanent in the way a crystal may be permanent. They are made and unmade constantly. Yet their chemistry is not arbitrary. It works because matter behaves with remarkable consistency. A protein folds because its chemical groups interact in repeatable ways. A membrane forms because certain molecules reliably arrange themselves in water. Hereditary information can be copied because molecular pairing follows stable patterns. This reliability becomes clearer inside the cell. A cell is not simply a small bag of chemicals. It is a regulated material environment in which countless reactions proceed without dissolving into disorder. Enzymes accelerate reactions that would otherwise be too slow. Membranes separate one compartment from another. Gradients of charged particles are maintained across thin boundaries. Structural molecules hold shape while still allowing movement. If the material world were not stable at this scale, metabolism could not proceed with such precision. There would be no lasting membrane, no repeatable protein folding, no faithful copying of hereditary material, no orderly exchange of energy. Life reveals that matter is able to sustain a controlled chemistry delicate enough for living organization. Living bodies also show how persistence can arise from turnover rather than immobility. Many molecules in an organism do not last for the lifetime of that organism. They are replaced. Proteins are broken down and rebuilt. Cells die and are renewed. Water and nutrients circulate. Even bone is slowly remodeled. The organism remains because the pattern persists while the components flow through it. This is a very different kind of endurance from the endurance of rock or ice. Yet it depends on the same underlying trust in matter. The replacement molecule must behave like the one before it. The new cell must build from familiar substances using familiar reactions. Life therefore depends not on unchanging material pieces, but on the repeatability of material law. Chemistry also ties living matter to the wider environment. Plants, algae, and certain microbes build organic molecule from carbon dioxide, water, and sunlight or chemical energy. Animals and many microbes rely on those products directly or indirectly. Decomposition returns material to soil, water and air, carbon, nitrogen, and phosphorus move through atmosphere, living tissue, water, and ground. A carbon atom may become part of a leaf, then a mussel, then soil, then dissolved carbon in water, and later return to the air. The living world depends on this circulation, and the circulation is possible only because matter remains dependable while changing form. For all its sensitivity, life therefore speaks strongly for material stability. A living system can be injured by heat, cold, radiation, poison, or starvation. A species can disappear, an ecosystem can collapse. Yet the chemistry of life itself demonstrates a deep continuity in ordinary matter. The molecules may be fragile in detail, but the rules that govern them are steady enough for cells to arise, bodies to develop, tissues to heal, and heredity to carry form across generations. In living matter, the long endurance seen in galaxies, stars, worlds, and rocks becomes intimate. It becomes breath, sap, blood, membrane, shell, wood, and tissue. These forms are transient, but their transience sharpens the lesson. Life is so intricate, so conditional, and so continuously active that it can exist only because ordinary matter is stable enough to support complexity without surrendering coherence. At the human scale, matter becomes ordinary enough to be overlooked. It becomes wood in a table, iron in a tool, salt in water, glass in a window, clay in a wall, and fabric in clothing. It becomes the ground beneath a step and the cup held in a hand. In this familiar region, the long endurance already seen in galaxies, stars, worlds, rocks, and living systems takes on its most direct and unremarkable form. Matter appears dependable because it behaves as though it has identity. A stone remains a stone when moved from one place to another. Water remains water whether it gathers in rain, sits in a vessel, or freezes in cold air. Metal can be melted, cast, hammered, and cooled. Yet it remains recognizably the same material through each change of shape. Human life rests on this constancy so completely that it rarely needs to speak its name. Everyday experience is full of quiet acts of trust in matter. A bridge stands because stone, steel, and concrete keep their load-bearing properties over time. A glass vessel holds water because the solid wall remains intact and the liquid behaves as expected within it. A blade cuts because its material preserves hardness and edge. A roof keeps out rain because wood, tile, metal, or other substance continues to resist weathering long enough to serve its purpose. A ceramic bowl does not become cloth by age, and a copper wire does not turn into sand through simple use. Human making depends on the expectation that materials possess stable characteristics: hardness, flexibility, density, transparency, brittleness, solubility, and conductivity are treated as reliable because repeated observation shows them to be so. This reliability is not perfect, and yet its imperfections strengthen the point. Wood swells in moisture and shrinks in dryness. Iron rusts. Paper burns. Water evaporates. Wax softens in heat. Salt dissolves. Glass can shatter. These changes are not signs that matter lacks identity. They are signs that matter behaves in regular ways under changing conditions. A substance responds according to its nature. Heat softens what is meltable. Cold stiffens what is freezable. Moisture alters what can absorb it, and air transforms what can oxidize. Even failure is patterned. A beam bends under too much weight because its strength has a limit that can be measured. A vessel cracks from sudden temperature change because the material expands and contracts within constraints that remain consistent. Matter proves trustworthy not because it never changes, but because its changes are ordered and repeatable. This is why everyday craft and engineering become possible. A potter shapes wet clay, knowing that it will hold form in one state, then harden in another. A mason chooses stone for compressive strength. A carpenter reads grain and density in wood. A metalworker heats, hammers, and cools a piece because the material follows predictable behavior. A cook relies on the thickening of starch, the melting of fat, and the boiling of water. A physician trusts that measured substances act in consistent doses. A builder, sailor, farmer, and weaver all proceed from the same underlying confidence. Matter can be known well enough to be used because it does not abandon its properties without cause. Measurement deepens this ordinary trust. Everyday matter can be weighed, compared, poured, cut, heated, mixed, and timed. A vessel filled to a certain level contains a predictable amount. A balance gives the same reading for the same object under the same conditions. A metal rod expands when heated and contracts when cooled by regular amounts. A dissolved substance changes the taste, density, or freezing behavior of a liquid in ways that can be observed again and again. Human knowledge of the material world begins here, not in abstract theory, but in repeated contact. Matter is handled, and it answers in stable patterns. The same grain of sand scratches the same softer surface. The same oil spreads in a similar film. The same wood floats while the same stone sinks. This repetition teaches that the world is intelligible because its substance is dependable. Storage is another quiet testimony. A jar can hold grain through a season. A sealed bottle can preserve liquid. A block of salt can remain in dry shelter for years. Stone monuments survive generations. Fired brick carries the labour of one age into the next. Coins, tools, vessels, and written surfaces can outlast their makers because matter retains form long enough for memory and use to extend beyond a single life. Human history would be shallow without this endurance. There would be no archive in clay tablets, no carved inscription in stone, no surviving wall, no preserved pigment, no metal blade dug from old ground, no shard that still reveals the shape of a lost vessel. Material stability allows culture to accumulate. Even the simplest acts of recognition depend on it. One object is distinguished from another because matter offers persistent qualities to the senses. Smoothness differs from roughness. Opacity differs from clarity. Weight differs from lightness. A fabric folds differently from leather, and water moves differently from oil. A person moving through daily life learns these differences not by formal theory, but by continuous encounter. Matter presents itself as a world of regular textures, resistances, and transformations. The hand learns it, the eye learns it, the ear learns it in the sound of wood, stone, metal, and glass under contact. Familiar life becomes possible because the same materials continue to answer in the same ways. In this region, matter is not remote or hidden. It is the nearest thing. It is cup, door, floor, dust, bread, ash, rope, paper, flame, and rain. It is the ordinary substance a habit, yet precisely because it is near, it reveals something profound. Human beings live as though the material world keeps faith with itself. They store, build, repair, preserve, and remember on that basis. They expect a vessel to remain a vessel, a wall to remain standing, and a measured quantity to remain what it is until some definite process alters it. Everyday life would be impossible without that expectation, and everyday life continues because matter justifies it at the human scale. Then, matter appears not mysterious but faithful. It can be worn down, broken, softened, dissolved, or transformed. Yet in each case it behaves through recognizable order. Familiar objects and familiar substances show that the stability of matter is not only a fact of stars and stone. It is present in the most ordinary contact with the world. The table, the cup, the blade, the window, the grain, and the rain all bear the same quiet message. Matter remains itself long enough to be trusted. At the atomic scale, matter becomes smaller than direct human sight, yet it grows more orderly rather than less. A familiar object that appears solid and continuous is, in this region, understood as an immense gathering of atoms. An atom is the basic organized unit of ordinary matter. It is the smallest part of an element that still preserves the chemical identity of that element. Gold remains gold because its atoms have a certain inner arrangement. Oxygen remains oxygen for the same reason. Carbon, iron, silicon, sodium, calcium, and every other element are distinguished not by outward appearance alone but by the structure of their atoms. This gives ordinary matter a new level of stability. The table, stone, cloud, leaf, and bone do not hold together merely because matter exists. They hold together because atoms preserve identity. An atom is mostly space. This is one of the quiet surprises of the material world. The atom has a tiny central nucleus, and around that nucleus are electrons, light particles that occupy regions described by quantum physics rather than simple little tracks like planets moving around a star. The central nucleus contains almost all the atom's mass. The electrons contribute very little to the mass, but they matter greatly for size, chemistry, and interaction. Because the nucleus is so small compared with the full extent of the atom, matter is not solid in the simple picture suggested by touch. It is structured emptiness held in stable form by the laws of nature. Yet this does not make the world insubstantial. On the contrary, it explains why matter can be both resistant and active, both spacious at one scale and solid at another. The electrons occupy allowed states, sometimes described as shells or orbitals. These are patterns of probability, regions where an electron is likely to be found. The language is technical, but the practical meaning is simple. Electrons do not sit anywhere at random. They are arranged according to definite rules. The lowest energy states are filled first, and higher states become available in ordered ways. This arrangement determines how an atom behaves when it meets another atom. It determines whether an atom tends to give up an electron, gain one, share one, or remain comparatively inert. Chemistry therefore begins here, not in large visible substances, but in the stable ordering of electrons around a small dense center. The size of the atom is set mainly by the region occupied by its electrons. The nucleus is far smaller. If the atom were imagined as vast compared with everyday life, the nucleus would still occupy only a tiny central region, while the electrons would define the broader extent. This contrast helps explain why matter can change shape, form bonds, conduct electricity, absorb light, and resist compression. The outer parts of atoms interact first. When matter is pressed, it is not solid lumps colliding in the simplest sense. It is structured atomic regions responding according to electrical and quantum rules. The sense of firmness felt in ordinary life arises from these interactions. The world is held together and kept apart by a stable atomic order, too small to see directly but reliable enough to build every familiar form. Each element is defined by the number of protons in its nucleus. This count gives the atom its identity. An atom with 1 proton is hydrogen. An atom with 6 protons is carbon. An atom with 8 is oxygen. An atom with 26 is iron. The number of electrons in a neutral atom matches the number of protons, and this balance gives the atom no overall electric charge. When electrons are lost or gained, the atom becomes an ion, a charged form that still belongs to the same element but behaves differently in chemical settings. This framework brings order to the diversity of matter. Many substances look different and behave differently, yet their variety emerges from combinations of atoms built on a small number of stable principles. Atoms also explain why matter can remain itself through many ordinary changes. Water can freeze, melt, and evaporate, but the molecules remain built from hydrogen and oxygen atoms. Iron can be heated and shaped, but the iron atoms remain iron atoms. Carbon can appear in soot, diamond, living tissue, or atmospheric gas. Yet the atom at the basis of each case remains the same element. The larger arrangement changes, and with it the visible properties, but the atomic identities endure. This gives matter a layered stability. A substance may change state or structure, while the atoms within it retain their own character. Much of the persistence already seen in rocks, water, air, life, and everyday objects depends on this deeper constancy. Atoms are also the scale at which light and matter begin to reveal a more precise relationship. An atom can absorb or emit light only in particular amounts, because its electrons can move only between allowed energy states. When such transitions occur, light of specific energies is taken in or released. This is why atoms leave recognizable lines in a spectrum. A distant cloud and a nearby laboratory can both reveal the same element because the underlying atomic structure is the same. The atom therefore acts as a small and dependable translator between matter and light. It gives the universe legibility. It allows astronomers to identify elements in stars and gas clouds, and it allows physicists to test atomic behavior with extraordinary precision. The reliability of atoms makes the wider material world readable. Even thermal motion does not erase this order. In a hot gas, atoms move quickly and collide often. In a cold solid, they remain bound in orderly positions while still vibrating slightly. In a liquid, they move past one another more freely. These different states of matter reflect changing atomic relationships, not a loss of atomic identity. The atom remains the enduring unit across these changes. A solid can melt and a liquid can boil, but the underlying atoms still preserve the element from which the substance is made. This is why matter can transform so widely while remaining materially coherent. The atom provides continuity beneath visible change. At this scale, the material world appears both delicate and exact. A minute central nucleus holds most of the mass. Electrons occupy ordered states that define size, bonding, and chemistry. Elements differ by a simple but profound rule of nuclear charge. States of matter arise from the ways atoms are arranged and how they interact. The world of ordinary substances, with all its variety, begins from this quiet architecture. The atom is small beyond intuition, yet it gives matter one of its strongest forms of persistence. It allows a substance to change shape, state, temperature, and arrangement while preserving the inner identity from which its material nature flows. In the atomic frame, matter no longer appears merely as substance that lasts. It appears as substance that lasts because it is organized. The atom is that organization in its first complete form. It is the calm boundary between the visible world of materials and the deeper hidden structure that supports them. Everything larger depends on it. Within its small and ordered extent, the durable character of matter becomes clear. Inside the atom, the nucleus forms a region of extraordinary concentration. Almost all the mass of ordinary matter is gathered there, within a space so small that the rest of the atom seems wide by comparison. The nucleus is built from protons and neutrons. Together these are called nucleons, a brief technical term for the particles that occupy the atomic center. Around this dense core the electrons define chemistry and size, but here, in the nucleus itself, matter takes on a different character. It becomes compact, crowded, and strongly bound. The calm persistence of ordinary substance depends not only on atoms keeping identity, but on nuclei remaining intact. Without the stability of nuclei, the elements would not endure, and the visible world would lose the material variety on which stars, rocks, oceans, air, and living tissue depend. A nucleus is held together in spite of a deep tension. Protons carry positive electric charge, and like charges repel one another. If electric force alone governed the nucleus, its protons would not remain packed so closely. Yet nuclei do remain bound. which shows that another interaction is at work. This is the strong nuclear force, often shortened in description to the strong force. In the nucleus, it acts over very short distances and overcomes electrical repulsion between nearby protons. It also binds neutrons and protons together. The result is a stable central structure that can persist for immense spans of time. The strong force does not reach far outside the nucleus in the way gravity does across planets and galaxies, but within its small domain, it is one of the most powerful agencies in nature. Neutrons play a quiet and essential role in this balance. They carry no electric charge, so they do not add to the electrical repulsion between protons. Even so, they contribute to the strong binding of the nucleus. In many elements, especially heavier ones, neutrons provide added stability by increasing the attractive strong interaction without increasing the charge-based strain. A nucleus, therefore, is not simply a cluster of protons pressed together. It is a carefully balanced assembly in which the proportion of protons to neutrons matters. Too many or too few neutrons can leave a nucleus unstable. In that case, the nucleus may change through radioactive decay, moving toward a more stable form. The existence of such unstable nuclei does not weaken the broader lesson, it clarifies it. Stability in matter is not random stillness, it is structured balance. The lightest nucleus is the simplest. Ordinary hydrogen has a nucleus made of a single proton. It needs no neutron to remain what it is. Add one neutron, and the nucleus becomes the heavier form of hydrogen called deuterium. Add another neutron, and it becomes tritium, which is unstable. In helium, 2 protons and usually 2 neutrons occupy the center. Carbon commonly has 6 protons and 6 neutrons. Oxygen commonly has 8 and 8. Iron often has 26 protons and 30 neutrons. These examples show that every element is defined first by its number of protons, but the internal stability of its nucleus also depends on how neutrons are arranged alongside them. The nucleus therefore gives each element not only identity, but a deeper internal condition. This inner condition has consequences that remain invisible in ordinary life, yet shape the whole material world. Some nuclei are stable for periods far longer than the age of the universe. Others are unstable and transform through predictable radioactive processes. In one case, a neutron may convert into a proton, with other particles emitted in the process. In another case, a proton may convert into a neutron under the right nuclear circumstances. Some heavy nuclei emit compact helium nuclei, slowly reducing their size. These changes are governed by precise laws, and they reveal that not every nucleus has equal durability. Still, the important fact for ordinary matter is that many nuclei are extraordinarily long-lived. The elements that make up water, rock, air, living tissue, and the bodies of planets are largely composed of nuclei stable enough to persist through deep time. Nuclear binding energy helps explain this endurance. When nucleons join into a nucleus, the total mass of the bound nucleus is slightly less than the sum of the separate masses of its free parts. The difference corresponds to binding energy, the energy associated with holding the nucleus together. This does not mean the missing mass has vanished into nothingness. It means the bound state is energetically different from the separated one. To pull the nucleus fully apart, energy must be supplied. To form it from separate nucleons, energy is released. This relation gives the nucleus a physical depth absent from simpler pictures of matter. The nucleus is not a pile. It is a bound system. Its endurance comes from the fact that its internal state is energetically favored in stable cases. The balance is especially clear across the periodic table. Light nuclei tend to be most stable when they contain roughly similar numbers of protons and neutrons. As nuclei grow heavier, more neutrons are needed to help offset the increasing electrical repulsion among the larger number of protons. Beyond a certain range, very heavy nuclei become increasingly difficult to stabilize. This is why some of the heaviest elements are radioactive and short-lived. Yet the elements central to ordinary matter lie largely in the stable or effectively stable domain. Carbon remains carbon, oxygen remains oxygen, silicon and iron endure. Their nuclei hold together with a reliability that supports everything built from them. The material order of the world rests quietly on this nuclear steadiness. The nucleus also shows that the word element carries two linked meanings. In one sense, it refers to chemical behavior, determined by the number of protons and the arrangement of electrons. In a deeper sense, it refers to a specific nuclear center, with a definite count of protons and a usually definite or limited range of neutrons. Atoms of the same element can differ in neutron number. These forms are called isotopes, a short term for versions of one element with different masses because their nuclei contain different numbers of neutrons. Some isotopes are stable, some are radioactive, yet even this variety remains ordered. It shows that the nucleus admits families of related forms, each governed by precise conditions of balance and strain. In the nuclear center, then, matter becomes denser, stronger, and more exact. The strong force counters electrical repulsion. Neutrons deepen binding without adding charge. Protons define the element. Binding energy gives the nucleus internal cohesion. Stable isotopes persist through immense spans, while unstable ones change in lawful ways. The visible world depends on this hidden success. Every stone, ocean, cloud, body, and beam of ordinary substance contains nuclei that remain intact long enough for larger forms to endure. The nucleus is therefore not merely the center of the atom. It is the quiet seat of elemental stability, where matter holds itself together under forces intense enough to make its lasting presence possible. Within the nucleus, one particle quietly defines the identity of ordinary matter. This is the proton. It carries a positive electric charge and serves as one of the basic building blocks of atomic nuclei. More than that, it gives each element its name in the deepest physical sense. A nucleus with one proton belongs to hydrogen. A nucleus with 6 protons belongs to carbon. A nucleus with 8 belongs to oxygen. A nucleus with 26 belongs to iron. No change in the number of neutrons can alter that elemental identity. No change in the number of surrounding electrons can alter it either. Those changes may affect mass or chemical behavior, but the proton count remains the central mark. In this way, the proton acts as one of the quiet anchors of visible matter. It does not merely sit inside the atom, it determines what kind of atom the matter is. This defining role gives the proton a special place in the material world. Ordinary substances differ from one another because they are built from different combinations of elements, and elements differ because their nuclei contain different numbers of protons. A grain of salt, a drop of water, a bone, a leaf, a stone, and a metal wire all depend on this fact. The oxygen in water is oxygen because its nuclei each contain 8 protons. The carbon in living tissue is carbon because its nuclei each contain 6. The calcium in bone, the silicon in rock, the iron in blood and steel, and the sodium in seawater all derive their elemental identity from the proton. Matter at the human scale appears varied and richly textured, yet this variety rests on a simple inner rule. The number of protons in the nucleus determines the element, and the element helps determine the material character of the world. The proton also helps maintain electrical balance within the atom. Its positive charge is matched in a neutral atom by an equal number of negatively charged electrons. This balance matters because it shapes how atoms interact. The nucleus provides the positive center that holds electrons in the atom through the electric force. Without that central charge, the electrons would not remain bound in the same way, and the atom would not possess the ordered structure on which chemistry depends. The proton therefore contributes not only to identity, but also to atomic integrity. It helps make the atom possible as a stable organized unit. A nucleus gathers mass and positive charge at the center, and the electrons arrange themselves around it. From that ordered relation comes the possibility of molecules, solids, liquids, gases, minerals, cells, and all larger material forms. Although the proton is very small, its influence spreads through every level of ordinary matter. In hydrogen, the simplest element, the proton appears alone in the nucleus and gives rise to the most abundant atomic form in the universe. In heavier elements, multiple protons gather with neutrons to create larger nuclei. As the proton number rises, the atom's chemical behavior changes because the electron structure changes as well. This affects bonding, reactivity, color, conductivity, hardness, and countless other properties. Gold is distinct from copper, carbon from nitrogen, and oxygen from neon because the nucleus at the center of each atom contains a different proton count. The proton thus acts as a deep organizing principle. It does not determine every property by itself. Yet without it, the structured diversity of matter would not exist. In ordinary matter, the proton is almost everywhere. Though it often goes unnoticed, it is present in the nuclei of the atoms that build rock, water, air, and living tissue. It is present in the hydrogen of the oceans and stars, in the carbon of organic molecules, in the oxygen of the atmosphere, in the silicon of minerals, and in the calcium of shells and bones. Every visible object contains countless protons packed into its atomic nuclei. Their small size makes them invisible to direct experience, yet their number and arrangement give matter its elemental composition. In this sense, the proton is not rare or exotic. It is one of the most familiar constituents of the world, not because it is seen directly, but because everything seen depends on it. Mass is also tied closely to the proton. The nucleus contains most of the mass of the atom, and the proton is one of the main contributors to that mass. Electrons shape chemistry and the size of atoms, but they add very little to the total weight of ordinary matter. When a stone feels heavy, when a body rests on the ground, or when a planet holds an atmosphere by gravity, the mass involved resides mainly in atomic nuclei, and a large part of that nuclear mass belongs to protons. The proton therefore helps give matter not only identity, but also substance in the most literal sense. It contributes to the weight and inertia of the material world. It is part of what makes matter resistant to motion, difficult to lift, and able to exert gravity. The proton's charge adds another layer of importance. Positive charge concentrated in the nucleus shapes the electric field that binds electrons. It also determines how strongly the nucleus attracts those electrons. As proton number increases from one element to another, the positive pull at the center changes, and with it the structure of the electron cloud. This leads to the great range of chemical behaviors seen across the elements. Some atoms readily share electrons, some tend to lose them, some tend to gain them, some scarcely react at all. These patterns are not arbitrary. They arise from the central role of the proton in defining nuclear charge. In this way, the proton reaches outward from the nucleus into the whole domain of chemistry, linking the hidden center of the atom to the visible behavior of matter. The proton also participates in the making of heavier elements inside stars. When hydrogen is fused in stellar cores, protons enter processes that help build helium and, through later stages of stellar evolution, contribute indirectly to the formation of still heavier nuclei. This means the proton is not only a static component of matter already formed, it is also part of the long cosmic history by which visible matter comes to exist in richer forms. Even so, in ordinary matter as it now appears in worlds, oceans, minerals, air, and life, the proton is best understood as a stable constituent of nuclei and a defining marker of the elements from which these larger forms are built. At this scale, the proton stands quietly at the center of material identity. It is small, charged, massive compared with the electron, and essential to the structure of the nucleus. It defines the element. It balances the atom through its attraction to electrons. It contributes to the mass of matter. It shapes the diversity of chemistry by determining nuclear charge. Every larger material form depends on these roles. The proton is therefore not merely one particle among many. It is one of the deepest anchors of visible matter, a small and constant presence within the nucleus that allows the world to be composed, varied, and materially real. The proton appears in modern physics not only as a building block, but as a deeply reliable one. Across all ordinary observation, it behaves as though it endures. No confirmed experiment has ever shown a free proton or a proton bound inside stable matter to decay. This quiet absence carries unusual weight. Many particles known to physics are unstable. Some vanish almost at once. Some last a little longer. Some survive for measurable intervals before transforming into lighter products. The proton stands apart from this pattern in ordinary experience. It does not reveal a natural tendency toward disappearance. It appears, instead, as one of the material world's most patient constituents, a particle so long-lived that all common descriptions of matter treat its existence as effectively permanent. This practical permanence shapes thought long before it is stated aloud. When a physicist describes hydrogen gas, rock, water, living tissue, or the interior of a star, the description assumes that the protons present continue to be there, unless they take part in known nuclear processes that preserve baryonic matter within the ordinary framework of observation. When a chemist names an element, counts atoms, or balances a reaction, the proton is treated as an unchanging core marker of identity. When astronomy reads ancient light from remote gas clouds and distant galaxies, it interprets hydrogen and heavier elements as matter that has endured across immense stretches of time. In each case, the proton's stability is not the main subject. It is the silent condition that makes the subject intelligible. The age of the visible universe strengthens this impression. Matter has remained present through about 13.8 billion years of cosmic history. Stars have formed, burned, and ended. Galaxies have merged. Planets have cooled. Minerals have crystallized and survived. Life has arisen from ordinary chemistry. All of this has unfolded in a world where protons appear to remain available as durable constituents of atomic nuclei. If the proton decayed readily on cosmic timescales near the age of the universe, the material record would look very different. Instead, ordinary matter persists. This does not prove absolute eternity, but it makes the proton seem extraordinarily stable compared with the lifespan of stars, planets, and civilizations. Laboratory physics reaches the same conclusion by patience rather than by direct witness of decay. Detectors containing immense amounts of matter are observed for very long periods in the hope of seeing a rare event that would reveal proton breakdown. These searches remain silent. The silence matters because it is measured, structured, and cumulative. It is not a vague lack of evidence. It is a repeated failure to find proton decay in experiments designed precisely for the purpose. The present limits imply that if proton decay occurs at all, it is rarer than any ordinary physical process encountered in daily life or conventional astrophysics. The proton therefore acquires a strange status. It is not proven immortal, yet it behaves with a steadiness so extreme that material science proceeds as though it were. This assumption enters basic conservation ideas as well. In ordinary processes, the amount of baryonic matter is treated as effectively conserved. Matter may change arrangement, binding, temperature, or phase. Nuclei may fuse or split under specific conditions. Particles may be exchanged in interactions, yet the count associated with ordinary matter remains stable in the familiar regimes of physics. The proton embodies this expectation. A cup of water remains water through freezing and melting because its nuclei endure. A mountain weathers to sediment because its atoms are rearranged, not erased. A living body grows and decays because matter circulates through metabolism, not because protons quietly disappear from the world beneath the chemistry. The proton's apparent permanence gives ordinary matter its continuity through change. There is also a conceptual calm in this stability. The proton is composite, not elementary in the older sense of being without inner structure, and yet it remains astonishingly robust. It contains motion, energy, and strong internal dynamics, but these do not lead to observed spontaneous collapse. Instead, the proton behaves as a settled bound state, one that resists disintegration under normal conditions with extraordinary success. This is part of why it feels so foundational. A particle may be dynamic within, and still outwardly stable beyond all ordinary measure. The proton shows that matter can possess deep internal activity without sacrificing its lasting presence in the visible world. The natural language of permanence often grows around such facts. Textbooks speak of stable matter. Daily reasoning speaks of lasting substance. Human craft assumes materials endure. Geological history assumes atoms remain available to be recycled across ages. Biology assumes elemental composition persists through inheritance and metabolism. None of these fields needs to begin by defending proton stability each time it is used. The stability is already woven into the background of coherent explanation. This is a sign of how strong the assumption has become. It is not an arbitrary habit. It is an inference grounded in everything that works when matter is described across scales. Even radioactive decay, which shows that some nuclei are unstable, tends to reinforce the point rather than weaken it. In many radioactive transformations, the proton remains part of the new nucleus, or appears in new configurations consistent with known nuclear rules. Instability exists, but not as a general failure of protons to endure. Instead, it is the instability of particular nuclear arrangements. The proton continues as a participant in these processes. This distinction matters. It separates the common and well-observed instability of some nuclei from the unobserved possibility that the proton itself may not be ultimately permanent. In everyday and established nuclear physics, the proton continues to appear as a reliable constituent even where larger structures change. Because of this, the proton becomes one of the deepest practical constants in the description of matter. It defines the element. It helps give the atom its central positive charge. It contributes much of the mass of ordinary substance. It remains present across the age of stars and planets. It survives in the chemistry of life and in the minerals of ancient crust. It is searched for in great detectors and not seen to decay. The result is a picture of matter built upon profound trust. Ordinary substance appears durable because the proton appears durable. The visible world holds together in explanation because one of its key inner anchors behaves as though time does not easily act upon it. In this region of the story, the proton's stability is not yet a puzzle to be opened further. It is a condition to be recognized. Matter as commonly understood rests upon it. The proton seems to endure beyond all practical horizon, allowing atoms to keep identity, nuclei to remain present, and ordinary substance to carry its history forward. For everything built from matter, this quiet endurance functions like a hidden promise. The world remains materially itself because the proton appears, with extraordinary persistence, to remain what it is. Inside the proton, matter reaches a level that is both more hidden and more surprising than anything seen at larger scales. The proton has already appeared as a stable constituent of nuclei and as the defining marker of the elements, yet it is not a featureless point. It has an internal structure. Modern physics describes the proton as a bound state made from smaller constituents called quarks, held together by particles called gluons. This language marks a shift in scale and in understanding. The proton remains one particle in the atom, but inside it there is motion, exchange, and tightly bound activity. Its outward stability does not come from simplicity. It comes from a successful internal order. The proton belongs to a family of particles called hadrons, a short term for particles built from quarks and governed strongly by the interaction known as quantum chromodynamics. The full name is technical, but the central idea is plain enough. Quarks are elementary particles in present physics, and they interact through the strong interaction. Gluons are the carriers of that interaction. Together they create the bound internal world of the proton. In the simplest picture, the proton contains 3 valence quarks, meaning 3 quarks that define its main observable identity. These are 2 up quarks and 1 down quark. Their electric charges combine to produce the proton's total positive charge. 2 up quarks each carry a charge of positive 2/3, and 1 down quark carries a charge of negative 1/3. Together they sum to positive 1. This simple picture is true as far as it goes, but it is not the whole interior. The proton is not like 3 solid objects sitting quietly side by side. Its inside is a dynamic quantum system. The valence quarks are part of the structure, but they are surrounded by gluons and by short-lived quark and antiquark pairs that continually appear and vanish within the rules of quantum physics. These transient pairs do not change the proton's overall identity, yet they contribute to its internal behavior. The proton is therefore better understood as a restless field-bound system than as a miniature mechanical cluster. What remains calm from the outside is deeply active within. Gluons are central to this activity. They carry the strong interaction between quarks, and unlike the photon in ordinary electromagnetism, they themselves also carry the relevant kind of charge for that interaction. This gives the proton's interior a special richness. The gluons do not merely pass between quarks and disappear from the picture. They also interact with one another. The result is a tightly coupled internal environment in which energy, momentum, and binding are shared across the whole proton. This is why the proton cannot be pictured accurately as a tiny box holding a few separate pieces. Its constituents are bound into one another's behavior so completely that the proton becomes a single stable particle through their collective state. One of the quietest surprises of this inner world concerns mass. It is natural at first to imagine that the proton's mass comes mostly from the masses of its three valence quarks. In fact, that is not so. The masses of those quarks account for only a small fraction of the proton's total mass. Most of the proton's mass arises from the energy bound up in the motion of quarks and gluons and in the strong interaction itself. This is a deep result of modern physics. The proton is heavy, in everyday particle terms, not because it contains three large massive pieces, but because the internal energy of its bound state contributes most of what is observed as mass. Matter therefore becomes substantial here through dynamic structure as much as through constituent ingredients. The confinement of quarks is another defining feature of the proton's interior. Quarks are not observed in isolation under ordinary conditions. They appear bound inside hadrons such as protons and neutrons. This behavior is called confinement, a short term for the fact that the strong interaction does not allow quarks to wander freely away as separate long-lived particles in the familiar world. When energy is supplied in attempts to pull quarks apart, the interaction does not simply weaken into separation. Instead, new particle pairs can be created, leading to new bound particles rather than to an isolated quark. This means the proton's constituents are not like stones in a pile that can be lifted out one by one. Their reality is tied to the bound state they inhabit. This bound state is what makes the proton composite and yet stable. A composite object in ordinary experience may seem easier to break than a simple one. The proton shows that this intuition does not always hold at the smallest scales. Its internal constituents are bound by the strongest known interaction, acting over the proton's scale, and the allowed configurations of that bound system give rise to a particle that can endure with extraordinary persistence. The proton stability is therefore not an accident of stillness. It is an achievement of internal law. Quarks and gluons do not undermine the proton's permanence. They make that permanence possible. The proton also possesses internal structure in how momentum and spin are shared among its constituents. Spin is a quantum property often compared loosely to angular character, though it is not ordinary spinning in space. The proton's total spin does not arise from one simple source alone. It reflects contributions from quark spin, gluon spin, and the motion of constituents inside the proton. This has been an important area of research because it reveals again that the proton's outward identity is a collective result rather than a simple sum of obvious parts. Even a property as basic as spin emerges from the deeper coordinated interior of the bound state. High-energy experiments help reveal this hidden interior. When particles are scattered from protons at very high energies, the results do not resemble impacts on structureless points. They reveal internal constituents carrying fractions of the proton's momentum. These experiments show that the proton contains partons, a term used for the effective momentum-carrying constituents seen in such collisions. In practice, these include quarks, antiquarks, and gluons. The exact distribution depends on the scale at which the proton is probed. In this way, the proton reveals yet another layer of subtlety. Its interior cannot be described fully by one static image valid for all situations. It is a quantum-bound system whose structure depends on how it is examined, while still remaining one stable proton in the ordinary material world. Inside the proton, then, matter no longer resembles solid substance in the everyday sense. It becomes a dense and dynamic bound state of quarks, gluons, and fluctuating quantum fields. Positive charge emerges from the combination of quark charges. Most of the proton's mass emerges from internal energy. Stability emerges from strong binding and confinement. Spin emerges from shared contributions across the whole interior. The proton is therefore both one particle and many interacting parts, both outwardly calm and inwardly active. Its enduring presence in matter does not require simplicity. It arises from a deeper and more intricate order. In that hidden interior, the reliability of ordinary substance rests upon a structure more dynamic than quiet surfaces ever suggest. The idea of proton decay enters physics not because it is seen, but because deeper theories leave room for it and sometimes strongly encourage it. Up to this point, the proton has appeared as one of the most durable parts of ordinary matter. It defines the elements, anchors nuclei, and seems to endure beyond every practical timescale known from direct experience. Yet modern physics does not treat that endurance as automatically guaranteed by first principle. Instead, it asks whether the proton stability is exact, or whether it is only an extraordinarily long-lived approximation. This distinction matters because a thing may appear permanent and still turn out, at a deeper level, to be only nearly so. The proton becomes a central case of that possibility. In the standard model of particle physics, ordinary low-energy processes do not cause the proton to decay. There is no direct renormalizable interaction in the theory that makes the proton simply fall apart into lighter particles under familiar conditions. For that reason, proton stability fits comfortably inside the working framework of known particle physics. Yet the conservation behind this stability is often described as accidental. This means it is not imposed as one of the deepest design rules of the theory. It emerges from the structure of the allowed interactions at the ordinary level. Physics therefore leaves open a quiet possibility. What appears conserved in the familiar theory may fail when a broader theory is considered. This is where baryon number becomes important. Baryon number is a counting rule attached to matter, built from particles such as protons and neutrons. In ordinary matter, each proton and neutron carries one unit of this count, while corresponding antiparticles carry the opposite. In the familiar world, this count behaves as though it is preserved. Reactions may rearrange matter, but the total baryon number remains the same. Proton decay would break that rule. A proton would turn into lighter particles that do not carry the same baryon count, and the total would change. Because of this, proton decay is not merely one more possible decay. It is a sign that a deeper principle governing matter is not exact after all. Theoretical interest in proton decay grows strongest in grand unified theories. These are proposals in which the separate forces of the standard model arise from a single more symmetric framework at very high energy. In such ideas, quarks and leptons are often placed into common mathematical structures. That change is profound. In the familiar standard model, quarks and leptons are distinct classes of particle, even though they coexist in the same theory. In many unified theories, that separation becomes less fundamental. New heavy particles can connect the quark world to the lepton world. Once such connections exist, a proton can in principle transform into lighter particles such as a positron and a neutral pion, or into other allowed final states, depending on the theory. The proton then is no longer absolutely protected. It is only protected by the enormous mass scale of the new physics, which makes decay exceedingly rare. This is the central reason proton decay is considered seriously. It is not that known matter shows signs of falling apart. It is that some of the most ambitious attempts to unify the laws of nature naturally predict that baryon number is not exact. A proton then survives not because decay is forbidden in the deeper sense, but because the responsible processes are so heavily suppressed that the lifetime becomes immense. The proton may endure far longer than stars and planets, and galaxies, while still not being truly eternal. Theory therefore turns stability itself into a subtle matter. A particle may be effectively permanent across all observed history and still be unstable in principle. The search for unification is not the only motive. Physics also carries a second deep puzzle: the dominance of matter over antimatter in the observable universe. The early universe, according to standard understanding, begins in conditions where matter and antimatter would be expected to appear in close relation. Yet the later cosmos is clearly matter-dominated. One of the general conditions long recognized as necessary for producing such an imbalance is baryon number violation. This does not mean that proton decay by itself explains the cosmic asymmetry. The full problem is more demanding and involves other conditions as well. But proton decay would demonstrate in the clearest possible way that baryon number need not be exact. For this reason, the idea carries significance beyond the proton alone. It touches the larger question of why the visible universe contains enduring matter at all. There is also an aesthetic reason the idea persists in theoretical work. Physics often seeks patterns that reduce many rules to fewer ones. If the proton were exactly stable, that fact might itself require a deep symmetry that remains perfectly respected in all circumstances. If instead the proton is only nearly stable, then the observed longevity of matter might emerge from a high unification scale rather than from an absolute prohibition. Many theorists find this possibility natural. It allows the visible durability of matter to be real and immense without being ultimate. The proton would then resemble a mountain in deep time, enduring beyond ordinary comprehension while still not lasting forever. At the same time, theory remains cautious. Not every extension of known physics predicts observable proton decay. Some models suppress it almost completely. Some violate baryon number in ways that do not lead directly to proton decay. Some are designed precisely to avoid existing limits. This means proton decay is not an unavoidable consequence of all physics beyond the standard model. It is better understood as one of the cleanest and most consequential possibilities opened by many serious theories. Its absence already shapes model building. Simpler versions of some unified ideas have been ruled out or strongly constrained because they would make the proton decay too quickly. The idea therefore survives not as unchecked speculation, but as a disciplined theoretical possibility under pressure from observation. What makes proton decay so powerful in thought is the scale of what it would mean. A single confirmed event would show that the proton, one of the deepest anchors of ordinary matter, is not absolutely permanent. It would show that the apparent conservation of baryon number in everyday physics is only approximate. It would show that quarks and leptons may be connected more deeply than the standard model suggests. It would point toward new physics at energies far beyond direct human reach. In this way, proton decay is considered because it sits at a crossroads where several major lines of reasoning meet. The nature of unification, the meaning of stability, the status of baryon number, and the origin of the matter-filled cosmos all lean quietly upon it. Within this inner theoretical region, then, proton decay appears not as an observed fact but as a disciplined possibility. The proton seems stable in every practical sense, yet deeper frameworks suggest that this stability may be a long-lived approximation rather than an absolute law. That possibility is enough to keep the idea alive. It is enough to make the proton more than a stable particle. It makes the proton a test of whether matter itself rests on exact permanence or on a far deeper, slower, and more fragile kind of endurance. To search for proton decay, physics moves from theory into watchfulness. It does not strike matter to force the process to happen. it waits. This is necessary because the decay, if it occurs at all, is expected to be extraordinarily rare. A detector must therefore contain an immense number of protons and observe them over long periods, while remaining quiet enough to notice a single event that would stand apart from ordinary background activity. The task is not simply to build a large instrument. It is to create a place where matter can be watched with unusual patience, shielded from many distractions, and interpreted with care. In this inner experimental region, the search becomes an art of silence, scale, and discrimination. This is why major proton decay experiments are built underground. Deep rock overhead reduces the steady rain of cosmic ray particles that reaches the surface of Earth. Even underground, backgrounds remain, especially from atmospheric neutrinos, which can produce events that mimic some proton decay signatures. The detector must therefore do more than sit in darkness. It must distinguish rare patterns in light or charge from ordinary interactions that arise naturally in the environment. The challenge is not only rarity, but resemblance. A true proton decay event may leave behind a small set of particles whose signals must be reconstructed from the detector response, then compared against known sources of background. The search becomes a problem of patient statistical separation guided by detailed physical modeling. One of the best-known instruments in this effort is Super Kamiokande in Japan, a vast underground water detector. It watches for Cherenkov light, the faint optical signal produced when a charged particle moves through water faster than light travels in that medium. From the rings of light recorded by its sensors, physicists reconstruct what kind of particle may have passed through, how energetic it was, and whether the event resembles one of the expected proton decay channels. For the classic modes long emphasized in grand unified theories, such as a proton decaying into a positron and a neutral pion, the detector looks for a distinctive pattern of light consistent with the decay products and inconsistent with known background processes. Years of observation have produced no convincing signal in those channels, leading to lower limits on the proton's partial lifetime that already exceed 10 to the 34 years in key cases. Other modes require different strategies. Some theories place special importance on channels involving kaons, especially a proton decaying into an antineutrino and a positively charged kaon. That channel is harder for water Cherenkov detectors because the kaon may be produced below the threshold needed to emit direct Cherenkov light in water. The search must then rely on secondary signals from the kaon's later decay and on careful timing and pattern analysis. Super Kamiokande has also searched for such channels and for related kaon-based final states without finding a statistically significant excess over expected background. This has pushed lifetime limits still higher and narrowed the space available to some theoretical models, especially simpler versions that predicted more readily observable decay. The next stage of the search expands both scale and technique. Hyper Kamiokande, also in Japan, is being developed as a much larger underground water Cherenkov detector with improved photosensors and significantly stronger discovery reach for proton decay. Its size matters because a larger fiducial volume contains more protons under observation at once, and improved instrumentation helps sharpen the reconstruction of rare candidate events. Dune, in the United States, adds a complementary approach with large underground liquid argon detectors, designed in part to search for nucleon decay while also pursuing neutrino physics and supernova observation. Different detector media favor different signatures. Water Cherenkov instruments are especially powerful for some modes, while liquid argon offers particular advantages for others, including detailed imaging of charged particle tracks. The search therefore no longer rests on one method alone. It becomes a coordinated watch across different technologies. What these experiments actually count is not abstract permanence, but events. Each possible proton decay channel predicts a specific final arrangement of lighter particles. The detector records light, charge, timing, and geometry. Reconstruction software then infers whether the recorded pattern matches an expected decay mode more closely than it matches an atmospheric neutrino interaction or some other background process. Efficiencies matter because not every true decay would be seen cleanly. Nuclear effects matter because protons bound inside nuclei do not decay in empty space. Their environment can alter the visible final state. Background estimates matter because even a nearly perfect detector must confront the fact that ordinary neutrino interactions occasionally imitate the desired signal. The search is therefore experimental patience shaped by theory, simulation, calibration, and repeated refinement. The result so far is disciplined absence rather than discovery. No major experiment has yet observed proton decay, and this non-observation has become one of the strongest guides in building theories beyond the standard model. Models that predicted faster decay in prominent channels have been ruled out or pushed into more constrained forms. The silence of the detectors is therefore not empty. It already carries theoretical force. At the same time, the search remains alive because even enormous exposures have not yet reached every plausible range of lifetime predicted by deeper frameworks. A process rarer than anything directly witnessed may still lie ahead, waiting for larger instruments, longer observation, or a channel better matched to a new detector's strengths. In this way, the experimental search for proton decay becomes a final test of material patience. It gathers huge amounts of ordinary matter, places them in deep silence, and watches for a single betrayal of apparent permanence. The water must remain clear. The electronics must remain quiet. The backgrounds must be understood. The observation must continue year after year, not because matter seems fragile, but because it seems almost impossibly durable. To search for proton decay is therefore to do something unusual in science. It is to examine the most stable visible substance not by breaking it apart directly, but by waiting long enough to see whether time itself ever persuades one proton to become something else. If proton decay is ever confirmed, the change it brings is not local or minor. It does not merely add one more unstable particle to a long list already known. It changes the meaning of durability in ordinary matter. Up to this point, matter has appeared stable across every visible scale. It has endured in galaxies, stars, planets, rock, water, living tissue, and familiar objects. At each inward step, the proton has stood quietly at the center of that endurance. A confirmed decay would show that this stability, however vast, is not absolute. Matter would remain long-lived, but no longer fundamental in its permanence. Its endurance would be revealed as temporary on a scale so large that ordinary thought scarcely reaches it, yet temporary all the same. This would alter one of the deepest habits of physical reasoning. Modern science already treats many forms as transient. Stars are born and die. Planets cool and erode. Organisms live and vanish. Molecules form and break. Even some nuclei decay. Yet beneath all these changes lies the practical assumption that the proton itself remains. A confirmed decay would move change into the very heart of ordinary substance. It would show that matter does not merely change arrangement, temperature, or chemical state. At the deepest visible level, it can also cease to remain matter in the familiar baryonic sense. The world would still be lawful, still intelligible, still stable over immense durations, but its apparent material foundation would no longer be exact. Baryon number would be one of the first ideas transformed by such a discovery. In ordinary physics, baryon number behaves as though it is preserved. Matter rearranges but does not cross that boundary. A proton decay event would show that the rule is not ultimate. It would show that what appears conserved in ordinary experience is instead an approximation that holds extraordinarily well at accessible energies and timescales. This would place baryon number beside other quantities once thought exact and later understood as limited by deeper structure. Physics would not lose order by this change. It would gain a more profound one. The visible world would become the long-lived surface expression of a deeper law in which ordinary matter is only conditionally stable. A confirmed decay would also bring unification much closer to physical reality. Many theories beyond the standard model suggest that quarks and leptons are not fundamentally separate in the deepest description of nature. A proton that decays into lighter particles would demonstrate that such a connection is not merely a mathematical preference. It would show that the boundary between the material constituents of nuclei and the lighter particles outside them is permeable under the right conditions. This would be one of the strongest signs that the known forces and matter types emerge from a more unified order at very high energy. Human beings might still not reach that energy directly in any laboratory, but the decay itself would act as a message from that remote domain. A single event in a quiet underground detector would point toward a far deeper coherence in the laws of nature. The significance would extend beyond particle theory into cosmology. The observed universe is matter-dominated. It contains stars, gas, dust, worlds, and live in chemistry rather than equal visible amounts of matter and antimatter. A confirmed proton decay would not by itself solve that asymmetry, but it would establish beyond doubt that baryon number violation is physically real. That would strengthen one of the necessary ingredients for explaining why the cosmos ends up with the material excess it now displays. In this way, proton decay would connect the deep interior of the proton to the large-scale history of the universe. The smallest observed betrayal of stability would illuminate one of the largest unresolved features of cosmic existence. There would also be a change in the way permanence is understood in ordinary matter. A rock would still endure for geological ages. A planet would still remain for billions of years. A proton lifetime measured far beyond 10 to the 34 years would mean that no human structure, no biological history, no planetary cycle, and no stellar civilization confronts proton decay as a practical threat. Yet conceptually, everything built from ordinary matter would become finite in a new sense. The final horizon of decay would no longer stop with stars, black holes, cooling worlds, or exhausted galaxies. Matter itself would belong to long decline. The visible cosmos would be recast as a realm of immense but not endless persistence. This would reshape the far future of matter. In many long-range physical pictures, if proton decay occurs, the remnants of ordinary baryonic substance slowly disappear over incomprehensible spans. White dwarfs, neutron stars, planets, dust grains, and cold dispersed atoms do not remain as eternal leftovers. They too would participate in the deep attrition of matter. This does not happen on any near-cosmic schedule. It belongs to epochs so remote that even the age of present stars seems brief beside them. Still, the principle matters. A universe with proton decay differs fundamentally from one without it. In one case, ordinary matter may survive indefinitely unless altered by other processes. In the other, its survival is only provisional, however overwhelmingly long that provisional span may be. The philosophical weight of this would be quiet but profound. Matter often appears to thought as the dependable remainder, the thing that outlasts form. Fire ends, but ash remains. Bodies die, but elements return to soil and air. Mountains wear down, but rock remains in new shape. Proton decay would move impermanence beneath even that reassurance. It would show that the material remainder is not final. Yet this does not diminish the grandeur of matter, it refines it. Ordinary substance would still be among the most durable things known, but its durability would no longer be mistaken for timelessness. Physics would gain a more disciplined sense of permanence, one measured not by absolutes assumed too quickly, but by lawful endurance set within still deeper change. There would also be a lesson in scale. Human intuition is poorly suited to lifetimes far beyond stars and galaxies. A proton that lives for more than 10 to the 34 years is, for all ordinary purposes, permanent. Yet physics is not satisfied with practical appearance when deeper structure may differ. This is why proton decay matters so much. It tests whether apparent permanence is ultimate or only extraordinarily extended. A confirmed event would answer that test with unusual force. It would say that the material world is even subtler than it seems. It would say that what looks foundational is itself historical, destined not for rapid ruin but for eventual transformation. At the end of this inward journey, matter appears more delicate in principle and more astonishing in practice. If proton decay is real, then ordinary substance is not an eternal bedrock. It is a long-lived condition of the universe, sustained across vast ages and vast structures, yet still part of time rather than beyond it. The proton would remain one of nature's great achievements of stability, but no longer its final guarantee. The visible world would stand revealed as something both more fragile and more magnificent than before not everlasting matter. But matter that endures almost beyond thought, then yields at last to deeper law. In the quietest view, this does not make the world smaller, it makes it more exact. Matter remains patient. It remains the substance of stars, oceans, mountains, air, and living bodies. It remains the bearer of history across deep time. Yet the mind, moving inward far enough, finds that even this patience may not be absolute. The stone, the sea, the leaf, the bone, and the distant galaxy all depend on a stability so great that it seems complete. And still the laws of nature may hold one more layer beneath it. That possibility does not erase the calm of the material world, it deepens it. A proton lifetime beyond ordinary imagination means that matter keeps faith with the universe for spans so immense that worlds rise and vanish within them like brief weather. What changes in the end is not the usefulness of matter, nor its beauty, nor its role in the making of structure. What changes is the meaning of permanence. The world no longer rests on something truly fixed. It rests on something extraordinarily enduring. So the inward path comes to rest in a gentler understanding. Matter is not less wondrous because it may one day fail. It is more wondrous because it lasts so long, binds so much, and carries so much history before that hidden limit is ever reached. In that long endurance, the universe builds galaxies, stars, planets, life, memory, and thought. Then, somewhere beyond all familiar ages, deeper law may speak again.